Unit 4 considers transient analytical modeling of groundwater flow. Transient modeling involves variation of the system with time. Water moves into or out of storage, so heads, pressures, and flow rates vary with time. Consequently, transient models require a starting condition from which the system can change with time. We call these initial conditions. You are familiar with simple initial conditions, such as the hydrostatic conditions assumed for the Tice equation. In such a situation, the result can be expressed as a relative value, that is, as a drawdown, rather than an absolute value of head. All of the analytical solutions that we explore in this unit begin with hydrostatic initial conditions. Later in the course, when we discuss numerical modeling, we will be able to establish more complex initial conditions. For now, realize that you must have a starting condition and focus on the transient character of the groundwater systems. As with the steady-state analytical solutions, there are many solutions available in texts and journals, but we can only review a few solutions in detail. It is most important that you understand that there is a basis for each solution. That is, assumptions, initial conditions, system geometry, boundary conditions, and the transient stress. Again, you can vary the parameter values and obtain different results. Think about what the results mean in the physical setting that is represented. Think about unique ways that you can apply the solution. Keep your eyes open for analytical solutions in your daily professional life so that you can call on them in appropriate situations. When you work with a new solution, consider its applicability to your problem. Be aware of the nature and magnitude of the error that will occur when your situation deviates from the basis of the analytical solution. When I say nature of the error, I mean, will the result be higher or lower than will occur in the field? One needs to consider what is conservative, realizing that the nature of a conservative answer changes depending on the perspectives of the person calculating the answer. For example, if you're evaluating drawdown resulting from a pumping well, on the one hand, a conservative answer may be obtained by using a high hydraulic conductivity in order to obtain the maximum area of impact. On the other hand, a conservative answer may be obtained by using a low hydraulic conductivity in order to determine the largest drawdowns that might occur near the well. So you see, conservative depends on the issue in question, and there is not one set of parameters that yield conservative answers. As a computer modeler, you should be able to write small programs such as the applets I am making available to you here. The graphics aren't a necessity, but the ability to code in some modern computer language is important for a modeler. It is not likely that you will write elaborate groundwater modeling code such as ModFlow, which we will use later in this class. However, the ability to write codes to manipulate your data or solve an analytical solution will make you a good hydrologist. I do not require you to write computer code in this course, but I do expect that you can set up a spreadsheet to solve simple analytical solutions or manipulate some data. If you plan to use models in your career and you lack programming skills, you should strive towards developing some basic programming skills. In summary, transient solutions require initial conditions and describe variation of the system with time. As with the steady-state solutions, take your time studying the transient solutions. A good conceptual, intuitive grasp of groundwater systems will improve your capability as a numerical modeler. Develop an understanding of the concept of a conservative answer. Finally, if you do not have programming skills, start thinking about how you will develop some basic skills soon.